Good morning, everyone. Thanks for the introduction. I do this presentation together with my colleague Piotr. We are from CERN, part of the big data engineering team. For the next 25 minutes, we talk about our experience of running Spark on Kubernetes on OpenStack for our physics data. So, little introduction about CERN. So, CERN is a European laboratory for particle physics. So, we try to answer questions basically what is the universe made of, why does particles have mass, why we cannot see antimatter today. This is the place where the web was invented by Tim Berners-Lee. It is also home to a large Hadron collider and 4 big experiments: Atlas, CMS, LHCb, ALICE. We are 22 member states and few more associate members. And a large worldwide collaboration. So, we are pretty diverse team there at CERN. The main mission of CERN is the smooth operation of LHC to deliver collisions and physics data for researchers around the world to do new discoveries. It's the largest machine in the world. So, it's 27 kilometers in circumference. It's 100 meters beneath the surface. We are on the border of Switzerland and France in Geneva. It's the fastest racetrack on Earth. So, basically the protons are accelerated at the speed of light and they are collided at 4 different points where the experiments are based, and the detectors there track the collisions and record the data. Obviously, we don't want any noise, so there is high vacuum inside the magnets. And during our lead ion collisions, which happen every December, it's like the temperature at the center of collisions is 100,000 times greater than at the center of sun. So how do we get the data? So, all the collisions that happen at these 4 different points, the detectors record the data. So, the physics data are aggregated at the CERN data center where the initial data reconstruction happens. So, to give you some numbers, we acquire around 12.5 petabytes of data per month, out of which 2 petabytes is accessed every day. So, this is both for writing and reading. I will not go through the other numbers we have. We also have a secondary data center based in Budapest, Hungary, that provides additional computing needs. And in future, we will also be doing some hybrid model where we do purchase cloud resources. So, the data at scale, in a broad view, we have 2 types of data. So, obviously, the physics data. Physics data was already large even before the big data term was coined. So, CERN has to develop some custom tools to store this and analyze this. So, this is 2 components here. Today, the big data, physics data is processed in the WLCG grid. So, this is worldwide LHC computing grid. And the root framework, so it's a data analysis framework, is used to analyze and process the physics data. So, in this area we are using Spark, and we are in the early state of prototyping to see if Spark can help to reduce let us say the time to physics for analyzing the physics data. So, we have another category of data which I call it as infrastructure data. So, the LHC machine has lots of devices which log data, let us say in IoT manner to our HDFS file system, and we also have monitoring data that is coming out of the services that are in the WLCG grid and also the CERN data center. So, in this area we are using big data solutions quite heavily. So, Hadoop, Kafka and Spark to process and analyze the data, and also in the streaming. So, coming to Apache Spark at CERN, so this is the current state of art. So, we have Spark running on YARN HDFS. So, where you have physically a bunch of machines allocated, and you also profit from data locality. In total, we have around roughly 2000 physical cores that are available, and this capacity is just for the infrastructure data. So, around 15 petabytes of capacity. So, this is very suitable for our stable and predictable workloads. So, I emphasize predictable. So, we know what our users will run, when they will run, and we have resources available for them. And these are physical machines that are allocated. So, which means there is no resource elasticity. So, we cannot scale up and scale down depending on the needs of the workloads, and the compute is coupled with the storage. So, this is not like a cloud native model. We also have ad hoc workloads from our physics users who are doing early prototype of using Spark for physics analysis. Today, we also run this on Spark on YARN. So we are seeing how big data industry tools can help CERN to do new discoveries. So we are thinking about new programming and analysis model for physics data. So here we have some data and operational challenges. CERN is going to a new phase after 2 years, what is called high luminosity LHC. So which means the number of collisions per second increases, which means the amount of data that we acquire goes up from 12 petabytes per month by another 20-30%. And there is also like need from some experiment collaborations to do on-demand generation of physics analysis tuples. Today this happens periodically every 3 months. So if you are not, if your data is not in these 3 months, you have to wait for the next batch to do the physics analysis and tuples. So we are also looking to see if Spark can help here to do the on-demand generation of the analysis tuples. So as I said before, we don't have resource elasticity. There is no isolation of workloads. So as you can imagine, Python is heavily used, and there are competing demands from the users on the packages that they need. And the physics data itself is not stored in HDFS. It's stored in a custom-built CERN storage system called EOS. And as I said, we are also looking at how the industry big data solutions can help in physics data analysis. So in the early state of prototyping, we have 2 use cases that we have tested. So one is called CMS data reduction facility. So this is like a large ETL. So users will mention some filters and projections which are called as cuts in the physics world. And then you need to generate what is called group analysis tuples. So as you can see, this happens today 4 times a year. Can we use Spark to do this on demand? So we have done initial proof of concept on our private cloud, which is OpenStack, and we were able to reduce 1 petabyte of data in roughly 6 hours. So we need to have some proof of concept before we go and build our infrastructure. And as you can imagine, in this physics world with the peer reviews, the reproducibility is key. And another kind of use case that we are seeing is interactive physics analysis using notebooks. So a lot of analysis only starts with about 1 terabyte of data, which most of them do it today on laptops. And with the advent of high luminosity LHC, the starting data sets for the physicist can go up to tens of terabytes. So for these people, it's nice to have like some distributed backend like Spark that can be connected to notebooks, where the computation can be parallelized and distributed. So here, as I say, we propose a time efficient way. So essentially reduce the time it takes to do the analysis. We also want to investigate the impact and usefulness of external solutions for HAP computing like Spark, and make a ready model for future analysis and for other people who are entering the research world to follow. So here, as you can see, we have done an initial test, scale test with Spark with a starting input data set of 4.7 terabytes. And as you can see, as I increase the number of cores, that is number of executors, we scale nicely, and at some point we flatten out. So this also looks very promising. So these are the challenges that we have going from analyzing infrastructure data to physics data. We need to have infrastructure that is ready for our users to use it. So we did some literature study. So cloud native approach, as you know by now, is an approach to building and running applications with that exploits the advantages of cloud computing model. So essentially you decouple storage from compute. You spin off your compute, which is your Spark clusters, as and when you need. You scale up and you scale down as per your workloads. So companies attempted cloud native Spark deployments using Kubernetes, which was like in the preview mode in Apache Spark 2.3. And when you go to this model, you lose data locality, and we see that nowadays with the network we have 10 gigabit and 40 gigabit and 100 gigabit that's coming in the future, is probably data locality is not needed for some use cases. We cannot say that it's definitely not needed today. And we also see that Databricks also benchmarking Spark with external storages like S3 and GCS. So how does it look? So as you can see on the left, you have like a monolithic system, that is Hadoop, that is coupled with Yarn, and Spark is running on Yarn. On the right, you see that you can run Spark on Kubernetes and access external storage, that is EOS, S3, GCS, Kafka, HDFS also. All this you could also do it with Spark on Yarn, but the point here is to have the resource elasticity. So like here Hadoop went in this direction because you assume that the disk bandwidth is higher than the storage throughput over the network. So you want to have a large aggregated throughput because you have the local disks. So in the other model, you assume that the storage throughput that you get from these mass storages is higher than the cluster disk bandwidth. So you have the limited elasticity in the Hadoop model, and in the Spark on Kubernetes, since the compute is not bound to the storage, you can go up and down. So this is less noisy with the Hadoop model because you don't have much traffic on the network. But if you go on the Spark on Kubernetes model, you have to be careful. Even though if your workload scales nicely, you could be a very noisy neighbor to other things that happen in your data center. So that's how it looks if you want to run Spark on Kubernetes. So you have Kubernetes resource manager, on top of which you can run Spark, and you can run a lot of other applications that are now supported on Kubernetes. So at CERN we have a private cloud that is based on OpenStack. So OpenStack nowadays allows you to create Kubernetes clusters using a container orchestration tool called Magnum. So which means that we go from a monolithic model, that is Hadoop Yarn, to a microservice model where the Kubernetes cluster is created using OpenStack container as a service. And then the external storage, since it's already we have EOS, so that's provided by the storage service, and we provide a monitoring service to monitoring the workloads that are being run on the Spark on Kubernetes. So we also use a Spark Kubernetes operator that was initially started by Google, and with significant contributions from CERN as well. So you could you can ask, why do we need the Spark Kubernetes operator? You could simply use Spark submit, but you let go a lot of functionality that is required. For example, if your executors want to access some authenticated external storage systems, you need to have these authentication credentials on the executors. With a simple Spark submit, you don't get it. So the operator brings the feature parity known from Yarn, all the things that you can actually pass from the driver to the executor, the files and the credentials and the Kerberos. And the Spark operator gives idiomatic submission, application restart policies, and you can have custom volumes. If you are not putting all your software in the images and you are loading it from an external volumes, you can mount these volumes on your executor containers. And these are the three models that you could have. So you could also choose the one in the middle, but since we have a private cloud that's based on OpenStack, we choose the one that's on the far right, where you have OpenStack cloud infrastructure, where the resources are made available using what is called OpenStack projects, and then we use OpenStack container orchestration tool, that's Magnum, to create our Kubernetes cluster, on top of which we deploy our Spark on Kubernetes operator, which allows for the Spark workloads to run. So I stop here, and then I hand over to my colleague who will explain a bit more on the Spark operator, and he'll also provide some more demos.
Hi. So let's go into evaluating Spark Kubernetes properties, which we just described, and maybe some demo. So how does whole compute elasticity works when you have your data separated? So you have like cloud infrastructure tools like OpenStack Site Cluster, and you can resize, create, delete your cluster, get authentication. Then if you want the Spark operator and history server, then you just use Helm and create, delete, update your Spark operator, control bus stream jobs. Spark operator comes with the tool which is called SparkCTL. It's a little Go library which basically allows you to submit your jobs defined in YAML file to the clusters. The actual code, the Spark submit is running inside the cluster. via Spark operator, and Spark operator customize this Spark submit for you on demand based on some kind of cluster default configurations and other things, which you define in the YAML file. And then this Spark submit will create drivers and executors and fetch container, the container which you defined in the YAML file for your job. So how this workload reproducibly works, so you know, all of you probably know the Docker containers. So this allows you to like package software and build isolated and reproducible environments across multiple infrastructures. How this management of Spark application works in Kubernetes, under Kubernetes and operator. So you have a YAML definition, you specify your image and things like that, and then you submit it to Kubernetes cluster, to the API server. Spark operator watches for events and then creates a driver. As Spark executors are communicating with external storage, just fetching required dependencies, or actually the data is external, and then you can monitoring is really a similar way. So how actually operator is built inside? So you have a Spark application control, which handles registers the submission. Then you have Spark runner, which executes actually Spark submit, so the actual binary or version of Spark. And then you have Spark monitor, which reports updates on pods to controllers. So it just watches what's happening in the cluster for each specific application. And then you have mutating emission webhook to handle customization of your Docker containers and the affinities. So you have to think, like, in this model, you don't have kind of persistent storage. In this model, current one, which is available for us at CERN, you don't have this persistent storage, so you have to find somehow different solutions. So they're available. There is network volume mounts, which is SEPFS, is like, and SEVMFS, which is like NFS kind of storage, which you can mount to your Docker containers. You can use it for software packages if you have large repositories of software packages, and then your workload just need to use a tiny selection of this. And then you can use it for checkpoints, even in history server. For file system connectors, you can use HDFS, external HDFS, as you probably heard from one of the presentations. And but we plan to use EOS since we have it. And this is good use cases for data processing, at least we think like that. And then you can use object storages also for data processing, events, and checkpoints. And for monitoring, we picked InfluxDB and Grafana because we already use it for different use cases. So how this memory management works? So from Yarn, we also know that the Yarn will also prevent some memory and disk failures. So Kubernetes does exactly the same. And you can also tune somehow these parameters. So Kubernetes will monitor memory and disk and detecting memory pressure and system mode of memory. You have more parameters to tune here. So we also did this scaling test on Kubernetes to actually see how it will go. So we picked just VM flavor, which has like 2 CPUs and 12 GB of RAM. Since our workload will occur to be RAM intensive. And then we did some scaling tests from 60 to 180 VMs, so we've been just resizing cluster. And then we did one load test, so we once resized it to 500 VMs, which ended up in 200 hypervisors. Essentially, it was just reducing data, and then you can do some Dimon mass calculation, and then this becomes small data set you can process further. We found that it was scaling pretty well. So when you were throwing more executors, it was linearly decreasing time. We didn't see much weird behaviors. What is important in this graph is that the throughput trend also increases. So while you put more resources, you have to see that the throughput will also increase linearly. And with 500 VMs, it was kind of significant. We also had, we overtuned one of the parameters. Let's call it a bug. And this actually resulted in a huge network traffic. And so you have to have your monitoring at hand, maybe alerting to prevent such situations and detect it early, since this could cause network congestions. So let's have a demo. So let's SSH to one of the VMs in OpenStack. And then we will just create one of the clusters. So we pick a project. Probably in other clouds you have this. You obviously have the same tools. Then you create a cluster. We pick like large flavors. Let's start with the nodes. We have some cluster template for Kubernetes. It creates a cluster, and then you can check the status of the cluster that is creating. So after some time, you can just fetch the configuration. It takes a few minutes essentially to create a cluster. So you fetch a configuration for the cluster. You can immediately access it. It says a version of Kubernetes, and then to install operator, you could already use the Spark to run the. You can already use Spark, but if you want Kubernetes, you have to init Helm, and then essentially, when Helm is initiated, you can deploy your package, actual Spark operator. So how do you do that? You just define the image of the operator, some versions, and then if you want some history server, you can customize it, and then you just use Helm install to use these values. This will create Spark operator. Spark operator is running in a few seconds, and this means you already have your Spark running. Yeah, so you have immediately you will have your history server running. Kubernetes dashboard, you can see what's happening in the cluster, and then there is also Grafana, so you can monitor what actually happened for this particular cluster, for the newly created one, whether you have some problems or not. So let's run some jobs. So sparkctl, there is no job running. Let's wait, what will happen? Okay, so you have your Spark application definition. It looks like this. So let's assume you have some Spark application, let's call it SparkPy, and then let's start with a simple one. So you have some examples, Docker image, which can be in the Docker registry. It could be protected with secrets. You define how big are the driver and executors, and then you run your application. This will create first driver in the cluster, Kubernetes cluster, and then allow you to watch what actually happens. So you can see that some driver is pending, then executors will be created, and then you can, for example, log what's happening. So you can go and see what's happening on the driver immediately. We can also run something more complex. So let's assume you have some local Hadoop config dir. You have some core site, which has some Hadoop configurations, I don't know, S3 credentials, things like that. So let's assume you have some more complex job, which has a lot of parameters. Just for this example, maybe some people from you know it. It's TPCDS, it's like a benchmarking tool. Then you define a lot of configurations which you need. For us, some memory overhead factor and some S3 committers and blah, blah, like just a simple one too. Simple, but also complex enough. And then you say that you want to submit together with this Hadoop config dir. And then essentially you can monitor the status, also see the logs. The logs will be also in the history server. I think I need to click now. Let's see. Yeah, so later you can just see the output because it's being streamed. You have some notifications that some data was sent to S3, some results. Then you have a Spark measure. It's a parallel section in one of the rooms. How you can debug your workloads, so you can attach to each the pieces of your code, and then you have your history server up and running together with dashboard. You can browse what actually happened in the cluster. I think this is the end for the presentation here. You can also delete I think there will be another thing. Of course, you can just now say, okay, let's have for nodes, for example. I'm finished with my big cloud. So, for example, you will run now interactive analysis, which is less intensive. In some cloud providers, you have things called autoscalers, but I will talk about it in a second. Okay, so conclusions, observations. This is probably an important fact. So OpenStack could provision Kubernetes cluster tens of nodes in automated fashions using cloud container engines. In other clouds, you also have cloud horizontal autoscalers, which could basically watch if you have some pod creations waiting and just add additional nodes when you need it. Kubernetes allows you to build this isolated and reproducible Spark with limited operational efforts. If you use Spark operator for your scheduled jobs or the ones which require some kind of maintenance, you might use Spark or Kubernetes operator. Then the important fact is data is external, so this has advantages but drawbacks also. So you have to think, do you need data locality? Why? Or is your data already in external storages? And is network important? And where do you run your workload? Then if the compute cluster is essentially managed service, so storage can scale separately from compute or in the cloud essentially. And there is another advantage that there is a storage interoperability. So we are a big organization, so we use all these storage systems for also different use cases than Hadoop, especially EOS. So this is also used by the grid and other operations, S3 too. So you can use the storage for different use cases, even the same data for the same different use cases than Hadoop. And without that collaterally, network can be a problem, so this could cause serious problem and bottleneck, which you need to have at hand with your monitoring tools. And large shuffle writes might be problematic because we assume here that you will have some compute VMs which are cost optimized or memory optimized, and these might not have large storage available. But on the other hand, you can have SSDs which can be used cheaply. So to accelerate the shuffle. And then multi-tenancy is still a question. We don't know how this will evolve. Kubernetes is extremely new. It's mature, but for data processing it's new for this use case. And we also did run, as you've seen on demo, the TPCDS benchmark, and we didn't see the particular overhead between, on the same hardware, on the VMs, on OpenStack and bare metal Yarn. There was a little bit only of change. And on Yarn, we had more spikes than in cloud Kubernetes. Probably you understand because it's Yarn, we have shared environment, so we have other workflows running. You share the environment, so you have to live with this. To give you this peak on the elasticity, so this cluster which we had had 40 nodes fixed. And on Kubernetes, we could just have, for a short period of time, 200 nodes and just shut down the cluster. And that's essentially the end of the story. Thank you. Do you have any questions? Yeah.
Hi, thank you for the talk. I was wondering, how do you monitor this infrastructure?
Yeah, so essentially we have this influx DB thing, which is like internally used. So we have some dashboards, and you can essentially know what's happening in the cluster. We also have the package called Spark Measure, which essentially you can hook to each job and then export some statistics and display them, or build alerting tools upon that, essentially. Also, Kubernetes dashboard allows you to export some, Kubernetes essentially allows you to export some additional statistics about the cluster itself, meaning network or usage of anything, literally.
Thank you, great talk. So I was about to ask about multi-tenancy. So,
sorry, what?
Multi-tenancy.
Multi-tenancy.
Multi-tenancy, yeah.
One of great side of Yarn is being able to merge resources when you are in when sharing clusters. So how do you think you can manage this?
Yeah, so the model here could be, because we are kind of maybe specific organization, so you have groups which might say, okay, we want a cluster, and then just use the clusters from themselves and basically resize on their needs. So because they know what they will use and how they predict the workloads. So this offloads from us these kind of problems. This would be interesting to actually investigate multi-tenancy. So if someone wants to share the cluster between multiple people, how this will all work. But essentially, this is just a problem of security, not of the actual work, because you can submit jobs, and this essentially will just be separate pods. So there is just question of how do you secure this whole thing. Yeah.
So one of your colleagues yesterday was talking about Spark MPI, and he wasn't able to elaborate more about what they're running that on beyond traditional HPC hardware as well as more interconnect. But is that something you're also running on this OpenStack Kubernetes framework?
This picture is.
It's Victor or?
Yeah, we don't have any experience on running Spark on MPI. So we could have an offline chat with our colleague who gave the presentation yesterday if you are interested in this direction.
Hi. I was wondering if you tried running multiple Spark jobs at the same time, and how did you make sure that resources were used properly according to the
Yeah, so your question is, so you submit multiple jobs, and how do you make sure that the resources are not idle, or? Okay, essentially it will, if you create too much, the workload will say you have insufficient resources, and it will wait for new resources. So essentially, if you have autoscaler, the situation is easy, because basically cluster will autoscale automatically. If you don't, yeah, you have to manually resize your cluster and observe what is the scope of your needs. Because I mean, if you run in the interactive mode, your needs are not probably that big. But this is also a question: how do you scale this kind of thing, and how do you share resources? It is a question also on Yarn: how do you predict the usage of your cluster, right?
Did you see any problems with that? Did you try it?
So we have not tried it. So Spark dynamic allocation with the Kubernetes autoscaler is something that we want to look at. Yeah. But we have not, because the OpenStack installation that we have at CERN today doesn't support the autoscaling of Kubernetes clusters.
Yeah, I think the dynamic resource allocation is not yet there available for Spark and Kubernetes, essentially, like a native implementation. So I'm not sure if you are asking about dynamic allocation or basically VM scaling.
Both.
There was a question, I think.
Last question. Yeah. Hi. The question was about the disaster recovery aspect for your infra. How does it work? How do you manage it?
So yeah, I mean, this whole thing is kind of experimental. So we try to guide how it might work or might not. You could build the federations and have your cluster on essentially another cloud even, or another infrastructure. Our OpenStack runs also on multiple availability zones. So you can spread your VMs across multiple availability zones. One can be in Hungary, the other could be in one part of the data center or in another part of the data center. And then essentially you can also set a pod affinities. So you can say, if the nodes here are available, I want to schedule there only. And then if they are not, you will schedule to another part of the data center. The guys from OpenStack were mentioning some preemption stuff. This could be also interesting, like how to run on preempted VMs. This could also open new doors for how to get resources. I mean, this is not directly connected to disaster recovery, maybe, but yeah. Essentially, you have to have two masters to handle this, right? So one master has to be in one part, one availability zones, another has to be another availability zone. So this is scheduler specific. So Kubernetes allows you to have multiple masters.
Okay, that's all the time we have. Thanks very much.